move to the third one, given by Dr. Mike Fluss from Lawrence Livermore National Lab. The title is Ion Beam Testing of Ferrite-Martensitic and Ferrite-Martensitic ODS, oxide dispersion strain materials for inertial fusion energy.
Is this on? I think it will be in a minute. Okay. Well, I'm going to use this. Thank you. First, at the risk of using up my 2 minutes left, I would like to thank the organizers for inviting me and giving me the opportunity to speak with you about materials testing, particularly motivated by inertial fusion energy. And we've seen this cartoon already. So our motivation right now is looking at ferritic martensitic steels, which are likely candidates for a demo-like IFE project. But we're also looking at the ODS variants, which are also candidate materials for improving the materials that are used for first wall and blanket in an IFE machine. Our approach for looking at these materials has been the use of TEM characterization of as manufactured materials, and where we developed some new ideas about the consolidation process for these ODS steels. Our primary way of testing materials is to utilize ion beams. Ion beams allow us to accelerate the aging process in these materials by as much as 3 or 4 orders of magnitude over what they would see in an actual fusion environment. We use both a dual beam, and when I say dual beam, I'm referring to helium and iron ions, using those, we've studied the helium sequestration mechanism, which is related to the whole process of cavity formation and swelling of materials. And then we've also used triple beam studies, where we used helium, hydrogen, and ions. And there, I'm going to tell you a little bit about hydrogen synergistic effects and some of the progress maybe that we are making on using micromechanical techniques in the post-irradiation examination of these irradiated materials. Probably the most important thing I want to talk about, and therefore I'm going to give somewhat short shrift to the items on the top of the list, is the whole question about can ion beams be a quantitative surrogate for neutrons? And can we use them in such a way that we actually can make early down selection and qualification of materials, reducing the risk and uncertainty, the risk primarily being an economic one, in the selection of materials? And can we, in fact, sort of pull ourselves up by our bootstraps, and by doing this type of analysis, actually bring ourselves to the point of having a demo inertial fusion energy machine that then can serve also as a materials test bed for developing more advanced materials for inertial fusion energy. At the heart of this, the physics of all of this, is the so-called rate effects, and that's what I'm going to speak about at the end of this talk. So as you heard, and I think the question that was asked over here about the question about can we use current materials. In the case of inertial fusion energy, the advantage is that we have a point source and that the optics that feed the lasers to that point source are completely separable from the first wall and blanket. There's no diverter issue in the case of inertial fusion energy. There are many other issues that do not exist in sustained plasma that do exist in inertial fusion energy. But the one thing that is depicted here is that in the Livermore design for the laser inertial fusion energy system, that's been studied for the last 5 or 6 years at Livermore. This chamber is conceived of as being able to be rolled out and replaced in a period of a few months on a scale of about once every 5, 10, 15, or 20 years, depending, of course, on economics and depending on the material's radiation tolerance. So the real question then is not what materials we can use, but given the existing menu of available materials whose initial properties are attractive for an inertial fusion energy first wall and blanket, is how long will those materials last? And is there anything that we can do in terms of their metallurgy to mitigate or extend their lifetimes? As I said, that becomes primarily an economic issue. So that's what we're going. That is the underlying motivation of everything that I'm going to speak about. Now, before I go on, let me say something about the use of ion beams for studying materials for nuclear energy systems. If one goes back and looks at the 50-year history of fission energy, I think you will discover, at least this is my opinion, that ion beams have basically provided the real understanding of the mechanisms of materials aging driven by radiation effects in these nuclear energy systems. Obviously, there are also mechanical effects and there's temperature effects as well, but these are all combined with the exposure to the fission neutron environment. Nevertheless, if you talk to someone who is involved in licensing a nuclear energy system and therefore developing materials or certifying and validating those materials and ultimately getting them past the regulatory agency, they will tell you that the only way to test those materials is in the neutron environment that looks just like the neutron environment that they're going to be used. When you think about the science behind that statement or that position, you realize that it's really a matter of trying to understand what is the difference between high dose rate experiments and low dose rate experiments. Can you extract physical information from high dose rate experiments that is relevant to the low dose rate environment that the material will be subjected to in the case of either a fission reactor or a fusion reactor? And on the other hand, as I said just a few moments ago, the use of ion beams has actually provided the physical insight into mechanisms. So at the beginning of this talk, or for the first part of this talk, I want to talk about those things that are relevant to inertial fusion energy and possibly to fusion energy in general with regards to ferritic martensitic steels and their ODS variants that we've learned about, phenomenology that probably will also be extant in the fusion neutron environment at much lower dose rates, and things that we need to worry about in terms of materials resistance to radiation effects, effects that could in fact jeopardize the use of those materials and limit their lifetime. But at the end, I want to then return to the issue of how do we do ion beam experiments at high dose rates, accelerated aging, and ultimately obtain results that a regulator or an engineer would accept in terms of qualifying materials for a particular nuclear energy system, such as an inertial fusion energy system. So this is just a quad. These are the materials that we're going to be talking about. This is the techniques we're using, multiple simultaneous ion beams. We also, this facility, by the way, is at CEA Saclay. It's a unique facility. There's only 2 like it in the world at this time, one in Japan and the one in France. And at Livermore, we use a 10 MeV tandem to do high-dose sequential irradiations. This, of course, is not simultaneous, where we inject helium and heavy ions in order to actually learn something about the underlying physics of what is happening when we do have simultaneous beams. Our primary methods of analysis are microstructural analysis, 3D atom probe, and we also are extending our capabilities to do small-scale micromechanical property measurements. The work is heavily supported by theoretical modeling, but I'm not going to have time to spend talking about what we've been doing in that area. The phenomena are interesting enough without that. Just some pictures of what goes on. This figure here is what our radiations at Saclay look like. Here, this blue line is the displacement damage as a function of depth into the material. That's from a 24 MeV iron ion injected into a iron-based steel, iron chrome, or an ODS alloy. The red curve is the implanted iron ions, and these two curves, the rectangular shape, the large one is the protons that are being injected, and as you see, we use a absorber wheel to spread out the depth profile of the protons, and here's the corresponding helium. Most of the irradiations are done with the helium atomic parts per million per displacements being in the range of between 10 and 40, and the hydrogen is always adjusted so that it's 4 times of whatever the helium value is. So typical expectation for first wall from N-alpha and NP reactions is 40 atomic parts per million hydrogen per dPa and 10 atomic parts per million helium per dPa. I wanted to talk to you a little bit about how the ODS particles are formed, but I really don't think we have time since I'm standing between you and your coffee, so I'm going to skip that. But let me talk about the helium sequestration mechanism that's associated with these nanodispersed particles that make up the ODS system. These nanoparticles, which you see here, notice the scale is about 10 nanometers in this TEM micrograph. These are primarily variations of yttrium oxide. The alloy is formed by ball milling or mechanical alloying, followed by consolidation at typically at a temperature of about 1050 degrees C. Now what you're seeing here is the result of an irradiation on a K3 ODS material that we obtained from Dr. Kimura in Japan. And if you look very carefully, you'll see some white dots around the periphery of this. Those are helium bubbles. And I'm going to expand on this a little bit. The first thing I want you to recognize is the result from an interesting experiment where we irradiated both an ODS material and an iron 14 chrome reference material simultaneously by rastering the ion beams, both the iron and the helium ion beams. This is a dual beam irradiation. And what you see is a textbook demonstration of the cavity growth model in the presence of helium. These models were developed in the 1980s by a number of people, but the analyses that we have done are primarily based on the work of Monser at Oak Ridge. And what you're seeing here is that in the case of the K3 ODS material, the helium has resulted in forming small, what we call them bubbles. And the reason we call them bubbles is that all of these cavities that are here are below what is called the critical size. The critical size is the radius at which the cavity transitions to a growth mechanism which is driven by a diffusional bias between interstitials and vacancies. Once you've reached critical size, this is an unconstrained growth process. In other terminology, this is called the incubation phase. And the more nucleation sites you have for these little bubbles, the longer that incubation phase will last, and the smaller the swelling per injected helium will be. So this is a technique. This says, let's put lots of small particles into a system and thereby stave off the possibility of rapid volumetric changes in the material. As I said, we simultaneously irradiated an iron-14 chrome specimen. This was about 40 dPa at 600 degrees C with a 40 atomic parts per million helium per dPa ratio. And here you see a bimodal distribution of cavities. These large cavities have made the transition to the above the critical size, and the cavities are growing in an unconstrained way. The material is starting to swell. Similar experiments that we've done recently on Urifer 97, which is a good candidate material for demo, and would also be a candidate material for a inertial fusion energy demonstration, tell us that at 10 atomic parts per million per dPa and 20 dPa, which is a fairly significant dose if you're thinking about fission energy, but for a fusion energy machine, it's a modest dose. We already have transitioned into the rapid growth regime. And so this immediately establishes, at least as far as the ion beam experiments are concerned, a maximum dosage and therefore a maximum time that the material can be utilized before you would have unacceptable changes in the dimensionality of the materials. Now, if you notice here, the densities of these cavities are shown here. And the density in the case of the ODS, where we have essentially are seeing the effect of what I would call a solid state surfactant, is an order of magnitude higher. Yet when we go and we count the number of ODS particles, we can't account for the number density of these small cavities. So where are these extra cavities nucleating? And what we discovered was that in addition to the ODS particles that we could see with an electron microscope or with 3D atom probe, there were also particles that we only became visible when they became decorated with helium. It turns out that the process of ball milling or mechanical alloying not only results in regions of, and then followed by consolidation, not only results in these obvious recrystallized particles, but it apparently also produces a large amount, actually an order of magnitude more, of particles that are so submicroscopic that they can't be observed in normal 3D atom probe or high-resolution TEM microscopy. Somewhat analogous to biological staining, but the helium, it makes it evident. And so this tells us now what the manufacturing process for ODS materials should be in the future to get the optimal management of the helium effect that ultimately leads to unconstrained cavity growth and dimensional changes. Now, one thing that is really very, very different about the fusion environment when it comes to radiation damage compared to the fission environment is the large amount of hydrogen that's being produced relative to the helium. The large amount of helium that's being produced per dPa is also very different. But this hydrogen synergistic effects is something that started to bother me when I saw data from Japan from, now it's almost 8 or 9 years ago, where they were irradiating F82H, which is another candidate RAF from reduced activation ferritic martensitic steel, which is a candidate for fusion energy as well. And they saw that when they irradiated with hydrogen, helium, and heavy ions, that they got 10 times the swelling that they got when they irradiated helium and heavy ions or hydrogen and heavy ions. So there was something synergistic going on. And these effects were taking place at temperatures where normally hydrogen would diffuse out of the material. And so suddenly the community divided itself into two parts. There were people saying, there's something wrong with these experiments. We know that hydrogen is a fast diffuser, and at temperatures of 500 degrees, which is where these experiments were done, there's no hydrogen in the system. Well, the Japanese actually showed that although they got an order of magnitude increased swelling in this synergistic triple beam experiment, indeed, when they went and analyzed for the hydrogen in the specimen, there was none there. So one of the lessons that one has to learn is that when you're thinking about a reactive species like hydrogen, unlike helium, which is not a reactive species, the effects that you can get aren't necessarily going to correlate with the amount of hydrogen that was in the material after the experiment was done. The hydrogen can catalyze processes in the series of rate equations that describe the system. Hydrogen can affect those and act as a catalyst for, in this case, cavity growth. So one of the questions that we decided to ask ourselves is, okay, this is happening in F82H. Does it happen in iron chrome, a reference material? The answer was yes. We see exactly the same type of extra cavity growth. The cavities look like the cavities that the Japanese saw. They had this hexagonal structure, et cetera, et cetera. But then we said, what about ODS? So I'm going to skip over this since I just told you about this. So, okay, what about ODS system? And when we went to look at ODS in triple beam effect, lo and behold, we saw something like what the Japanese were seeing in the F82H and what we were seeing in iron 14 chrome, but it turned out that on analysis, this was not what was really going on. This was not just simple cavity growth, acceleration of the cavity growth, either through changing the critical radius or changing the helium uptake. We don't know what the mechanism is. This is something else. And what we started to suspect that this was it was somehow related to another phenomena that had been discovered by several labs, but particularly at CEA. This had been discovered in reactor-irradiated ODS materials, that there's a halo effect formed, that if you irradiate at high temperatures, at intermediate temperatures, you discover, and then quench the specimen, you discover that the ODS particle has a halo around it. And what this halo appears to be due to is ballistic collisions that have decomposed the yttrium oxide, creating free oxygen, which then, if the temperature is high enough, recrystallizes over a period of time and can be made to disappear. But what this implies then is during the irradiation period, there's free oxygen in the system. Just like there's a steady state population of vacancies and interstitials during irradiation. Remember, radiation damage is a non-equilibrium process. And so there's a lot of things going on. This free oxygen is interacting with the hydrogen. And now you see some high resolution pictures of these infected voids, we call them. But it turns out there's no hydrogen there. But what it turns out from doing diffraction analysis in the high-resolution microscope, we actually were able to identify that these were hydroxides. At first we thought, oh, maybe these are iron hydrides, but they weren't. They had similar characteristics, but it turned out that this is some form of hydroxide. This is bad news, because these hydroxides embrittle materials very quickly. So now we have an effect that we really have to worry about. Is it dose rate dependent? And that's why we started thinking about dose rate effects. Will this go away in a fusion device? Is this something that's unique to the ion beam experiments? So dose rate becomes the issue. Are we looking at a real phenomena that will hold up under a 3 orders of magnitude difference in dose rate? I'm going to skip over the work on the micromechanics. And I want to go to the dose rate effects and finish up there. Okay, so I think I've said some of the things on the left. Ion beams are a knowledge generator. They tell us about mechanisms, and with that knowledge, we can learn more about how to manipulate materials, mitigate effects, improve them, et cetera, et cetera. But what about dose rates? So now I'm going to talk about a material that you're not going to build a reactor out of, silicon. A colleague of mine did a very interesting experiment at Livermore, and when I saw it, I basically, this is one of those things is, why didn't I think about this? Was my first reaction. And what he did is shown here, and I'm going to explain it to you. What he did is he irradiated with argon ions, so that's a fairly heavy ion, single crystals of silicon. And but he did this with a pulse beam. The beam on time was 1 millisecond, and this is about, I think, about 10,000 pulses. And the thing that was varied in the experiment was the time between the pulses, the T off. So the period was being varied. What this does now, and then after he gets done with this irradiation of a fixed number of pulses, so that's a fixed dose, he analyzes the damage by doing a channeling study. But there are many other ways you could analyze the damage. You could do resistivity, you could do microscopy, you could do a lot of different things. You could even measure some mechanical properties, whatever you like to do. And here's a plot now. So these are all for the same dose, but with the time off being varied. And lo and behold, he gets a beautiful second-order kinetic curve, which he then extracts a number which turns out to be about 4 or 5 milliseconds, which is essentially what's called the dynamic annealing effect. So what he's done here is over 2 orders of magnitude, he's been able to measure the kinetics associated with the interpulse relaxation. Now, when you think about it for a moment, you realize that ion beam, any type of radiation damage, is intrinsically a pulsed effect. Because if you reduce yourself down to a single particle, it's a pulse. They aren't spread out equally in time, okay? They come randomly in time. But the fact of the matter is that what we're dealing with is the formation of a damage cascade and its relaxation. Now, the proof that this is relevant comes in this figure over here. And so now I have both figures. On the figure on the right, the pulse data, which is these red dots over here, are the blue dots over here. And now it's being plotted in terms of the average dose rate, okay? Remember, these are, again, every point is all the same dose. So the only thing that's changing is the dose rate. So if there's 10,000 pulses, here they're done very quickly, and here they're done very slowly, but it's the same 10,000 pulses. And what you see is then he did as the corresponding experiment with a continuous beam, not pulse, at that same dose rate. And what you see is, by and large, these are as close to collinear as one can expect from this experiment. And that's exactly what you would expect. And in fact, now going back in the literature, Trinkhaus and others have written papers about this and predicted that in order to see differences due to the pulsing, you would have to go to such high intensities that it becomes almost moot whether that's relevant to anything that you're interested in with regards to radiation damage in nuclear energy systems. It would almost have to be a nuclear explosion. So it turns out that pulse data, and this is the sort of insight that my colleague Sergey at Livermore had here, is that pulse data basically imposes a time axis on the experiment and allows you then to extract kinetic data. Okay. Now that is very encouraging. That says we should be able to extrapolate, if you will, over 3 orders of magnitude by doing similar types of experiments on materials of technological interest in fusion energy. But then I'm going to tell you a secret. So these are all the things that I think we've learned so far. So this is the learning aspect of ion beams. What do we need to learn? Are the hydrogen synergistic effects strongly dose rate dependent? I'm hoping they are. There's reason to believe they might be, and that means that it's a red herring in our terminology. It's something that we don't really have to worry about, but we're worried about it with regards to materials, the applicability of these oxide-based nanoparticle distributions. So, are there adjustments that we can make to the Rathrum steels to mitigate the effects of hydrogen on increased cavity growth? We don't know the answer to that. We don't even fully understand the mechanism. So there's another research. This is, okay. Now, there may be a path forward to resolve dose rate question, and I think I just talked to you about that, and eventually make ion beams into, I should have the word, a quantitative surrogate for neutrons. That would be really groundbreaking, because today it takes 20 years to qualify a material for a nuclear energy environment like a fission reactor. Why does it take 20 years? Because part of that cycle has to do, part of that time scale has to do with going back and forth into reactors and doing post-irradiation examination, where the radiations take years to do. And if we can cut that down to days or weeks to do those irradiations, that would be just a whole game-changing thing in terms of materials development. But now here's the dirty secret that I want to end up with, and the dirty secret is this. While I believe that there's a path forward for extracting the kinetics and therefore making predictions about dose rate effects, if you're doing high doses, so for example in a steady state plasma machine, you're talking about materials lasting for 200 dPAs, right? That's a number that you hear thrown around. While that material is being irradiated, its microstructure is changing continuously. And the kinetics of what happens to the damage cascades that are being produced by neutrons depends on that microstructure. And so if you're going to do ion beam accelerated experiments that are quantitative, you have to have some idea about how the microstructure is changing underneath you and do those kinetic studies as a function of that microstructure. Okay. We believe that there's a way to do that, but the proof of that is going to come from doing the correct type of experiments. Now, let me tell you what the wrong experiment is. If you're interested in 200 dPa of damage, or in the case of an inertial fusion energy machine, 20 dPa of damage, which seems to be a good number, in terms of economics and materials, properties of materials that exist today. I like unobtainium, by the way. We've tried to make it several times. The wrong experiment is the following. We take a material, put it into a neutron environment, a fast reactor, and irradiate it so you have 200 dPa of damage in that material. You might even inject helium using either boron or nickel trick. There's some tricks for simultaneously injecting helium, so you can do the equivalent of a dual beam experiment in a reactor. And then to do the same experiment with ion beams. Instead of it, and the 200 dPa, if you were in Bohr 60, would take you 10 years, approximately. Bohr 60 reactor gets 20 dPa per year, so it would take you 10 years. You pull that out, and then you go to Saclay, and you do the same 200 dPa's in 2 days. And now you compare the two. If they agree, you should have gone to Las Vegas, because you are a very lucky person. But the chances are they will not agree at all, and you'll have no idea why they don't agree, because that's the wrong experiment. You have not taken into account anything having to do with the continuously changing microstructure. So that's where I'm going to end.
Well, thank you very much, Mike. I think if there is no, Well, please remember that we have only one question. No more, because if not, everything is delayed, okay?
But I'll answer questions afterwards.
So, who? Is some question?
Yeah, right there.
Okay, right there, okay.
Thank you, Mike, for a very clear insight in the comparison between ion and neutron for damage in materials. Of course, all of us would like to have a possible extrapolation route and use ion beams extensively. One might be tempted, in order to accelerate the dose, to increase the intensity of the ion beam, and one might have thermal effects due to these beams if we go too high in intensity. Did you evaluate the effect of this thermal effect?
Yes.
Because you could also get an extra thermal annealing contribution. Is this important factor or not?
Yes. Depending on the ion that you're using and the energy that you're using, there's a significant amount of electron hole pair production. Only about, so in the case of, for example, let me talk about a specific case. In the case of iron ions injected into iron at 24 MeV, which is what we're doing, only about 7% of the energy produces ballistic collisions. So you have heating along the path of the ion. Now, it's so close to the surface, and if you estimate the conductivity of the alloy that we're using, we monitored and controlled the temperature with infrared camera. And so we knew what it was. We also could monitor with corresponding thermocouples on the front and back sides of the specimen, the temperature rise from the beam. And so we did sort of the front end of the kinetics experiment that I was showing you to make sure that the dose rate effects, that there was no dose rate effect which we were going to attribute primarily to temperature. Okay, but it's more complicated than that, because now you got two variables. You have the temperature effect, and you have the actual dose rate effects. And the physics is somewhat orthogonal. I think now that we have an understanding of how to get at the kinetics, controlling the temperature is very, very important. And it may limit us to the maximum dose rate that we can ultimately go to. One of the big questions that has been left unanswered, but it gets revisited every 10 years, every time a new group of graduate students comes in, is what is the consequences of the heating along the ion track from electron hole pair production? How is that affecting diffusivities and other aspects? This is a particularly interesting problem in the case of fission fragments in the fuel itself in a fission reactor. So, good question.
Okay, thank you very much again to all the speakers.